Good morning, students. Welcome to today's lecture. Today we're going to start our lecture by analyzing the Fourier analysis of the inverter. Last day's class we have learned about what is single phase inverter and what is three phase inverter. Now here in this case what we will do, we know that if we convert a DC source to a AC source, that means a DC to AC, it is directly not converted to a pure sinusoidal wave. Rather, it will convert as a square wave. That means there are harmonics present inside those waveform. So suppose this is a waveform from a single phase half bridge inverter. If we analyze this waveform, then we'll find out that this is a DC part of that waveform. This is the fundamental one, and then it is comprises of different harmonics. Now among this waveform, this one is the desirable waveform. That means this type of waveform we want close to this type of waveform, and this type of waveform are undesirable. Now if we make a summation of this voltage, we can write that this is suppose the voltage, the output voltage. This can be write as the V0. This is the out DC component, and this one is your sinusoidal component, that is the fundamental component, and this is are the harmonics. Now here I have written all the second, third, all the harmonics. Now if we take the RMS values of this waveform, it will be look like this. And then if we goes on following this is the total RMS value of the total waveform, and this is the fundamental RMS value. So your harmonics will be is equals to V0 RMS square minus the fundamental RMS square. So this part is desirable, and this part is the, and other part is the undesirable. So if we take V01, so it will gives this thing is known as your total harmonic distortion, VOH by V01. Okay, this ratio is known as total harmonic distortion, where G is known as the distortion factor. Now if total harmonic distortion is 0, that means your VOH 0, that means it is a pure sinusoidal wave and your distortion factor is 1. And if the distortion factor is less than 1, that means your VOH and total harmonic distortion is there. That means it is distorted wave. And the value of the G is mainly lies between 0 to 1. So this will help us in analysis of the Fourier form to our single phase half bridge inverter. This is the general one. By using this, we can analyze the Fourier analysis for the single phase half bridge inverter as well as for the full wave inverter. This is very necessary because it always know since that when you convert AC to DC, there must be containing of the harmonics, because it is very impossible to eliminate all the harmonics. And to calculate, by calculating this THD, we can design our filter as per the requirement of the THD. That means what amount of harmonic distortion is there, as per the requirement of that we can design that thing. Okay, now this is the, we will now check for half bridge inverter for R load. What will be the total harmonic distortion? What amount of harmonic it is distorted? We know that this formula has already been derived in the last class. So from this, if we take the fundamental component, this is your fundamental component and this is your fundamental current. So if we take the RMS value of this, which is known as Vm by root 2, this is your RMS value and this is the RMS value of the current. Now for the single phase half bridge inverter, if we go, we know that the previous formula G is equals to V01 RMS, that is the fundamental component RMS value, by total component RMS value. That means V01 RMS by V0R. Okay. So from here, as we can see that the fundamental component RMS value is your root 2 VDC by pi. Now how this come? For a square wave, if we want to find out the RMS value of the square wave, we know that for RMS, you have to first find out the average. Average can be written as area by T. So its area is, if we square this one, that means this one, this plus this, then it will becomes as V square by 4. If we square this wavefront, then it will look like Vs by 4. So this area is equals to V square by 4 into T by T. So your average will be Vd square by 4. Average of this area is, this will be VDC. Sorry, this will be VDC, not Vs. This will be VDC. So VDC square by 4. So RMS equals to under root of the average. So that will comes as VDC by 2. This has been written here, VDC by 2. So if we calculate, your G is look like this and your TSD is nearly about 48% for a single phase half bridge inverter. So according to that, you have to design the filter so that we can get as close as the sinusoidal wave as we can get. Now, this formula is very much essential for your MAC syllabus as well as for your GATE syllabus also. This formula is various types of maths has come. So then we'll come to the power across the load due to the fundamental. First, we'll see that total power. This is the total power V0 RMS, that means the total voltage into I0 RMS into cos phi. Now we know that for a resistive load, cos phi value is 1 because voltage and current in the same phase. So your total power will be equals to V0 RMS into I0 RMS, that is equals to VDC square by 4R. Now, whereas for the fundamental case, V01 RMS into I01 RMS into cos phi 1. Cos phi 1 is the voltage, is the power factor, is the angle between the voltage and the current. Okay, so this is your cos phi 1. So from here we can find out that it is root 2 VDC by pi. Your V01 RMS and I01 RMS is root 2 VDC by pi r. So from there, if we multiply these two, we will get the fundamental power. So please don't confuse. There will be a fundamental power. It can be sometime it is required, and your total power, if you find out, just the difference is V0 RMS to I0 RMS, that is the total voltage into current into cos phi, and here it is the fundamental component, that is V01 RMS and I01 RMS. Okay, so here if we see that this is the single phase, this is the single phase. Wait 1 minute. This is the single phase. This is the waveform for the single phase half bridge inverter. As you can see that this is our V0 V0 and this is the fundamental component. That means we want to get from the square wave to the sinusoidal wave as possible. And this is also for the current. And this is your supply voltage. That means this is the voltage which you are getting from IS part. This is not so much important, but this too is very much important because this is your output voltage waveform, and we are looking to get this kind of waveform, and also we are getting this kind of output current waveform, whereas we're looking this kind of output current waveform. So that's why it is very important to know what amount of harmonic is distorted due to the inversion of the AC to DC. Okay, so from this thing, there are mainly three things we have learned. One is what is the total number of THD, total harmonic distortion, how it is calculated for us. Suppose any waveform, it is calculated like this, and then if we apply that in case of single phase half bridge inverter, it will be your distortion factor is like this, and your total harmonic distortion is nearly about 48%. And also we find out that what is the power across load for a single phase half bridge inverter, total power, and your fundamental power. So this harmonic, to find out the total harmonic distortion, it is very important, because as per the harmonic distortion of a inverter, we will design our filter as per the requirement of that. So this distortion is very much important. Students, if we have any doubt regarding this topic, you can ask in the comment box, and you can submit your assignment within today. I will not give you the time. Within today, after seeing this lecture, I am providing you the link. After that, you can submit your assignment. And as per the today's class, I will give the question in the IMCRP also on the basis of today's class. That means if you hear the today's class, then you can only answer those questions. Okay, your IMCRP code will also be circulating via your WhatsApp group. And if you couldn't understand anything, you can write in the comment box, and if I able to clarify those, I will try my best. But if it is not counted like that, then you are free to call me in my WhatsApp number. Okay, thank you.